Ever stop to think about what your smartwatch and a giant supercomputer that predicts the weather actually have in common? I mean, they're both computers, right? But they live in completely different universes of power and purpose. In this explainer, we're going to build a kind of mental map to classify pretty much every computer you'll ever run into. Seriously, think about it for a second. One fits in your pocket, the other fills up a building. One is for you, the other is for, well, all of us. But deep down, they share the same digital DNA. The trick is knowing how to categorize them, and that's exactly the journey we're about to go on. So here's how we're going to tackle this. We're going to look at computers from three totally different angles. First up, their sheer scale, from tiny to truly massive. Then we'll get into the nitty-gritty of how they actually speak or handle data. And finally, we'll look at what they were built for in the first place. When we're done, you'll have a complete framework to understand the whole lot of.
Okay, let's kick things off with the most familiar way of thinking about computers, their physical size and their raw horsepower. This is a journey that'll take us from the personal to the absolutely planetary.
This is the world you and I live in every single day. Microcomputers. The key here is that they're built around a single microprocessor and designed for a single user. We're talking about your desktop PC, your laptop, your tablet, and yep, the smartphone that's probably within arm's reach right now. These devices completely changed the game.
All right, let's take one step up the ladder. We've got mini-computers, or what people often call mid-range systems these days. The big idea here is that they're designed to serve a bunch of people at the same time. Dozens, maybe even hundreds. Think of a server at a small company running a shared database. Now, to be fair, modern PCs are so powerful that the line is getting kind of blurry, but the whole multi-user thing is still the key difference.
And now we enter the big leagues. Mainframes. These things are the unsung heroes of our entire global economy. They are colossal, unbelievably reliable machines built for one thing: bulk data processing. When a bank processes millions of credit card transactions every minute, that's a mainframe. When an airline manages its worldwide reservation system, mainframe. They just work 24/7, supporting thousands of users without breaking a sweat. And at the very top of the mountain, you'll find supercomputers. These are the Ferraris of the digital world, blazingly fast and wildly expensive. But here's the crucial difference. A mainframe is a master multitasker, juggling millions of simple tasks. A supercomputer is like a laser beam. It focuses all of its incredible power on solving one single, mind-bendingly complex problem, like simulating the explosion of a star or mapping the entire human genome. So you see the trend here, right? As we climb this ladder, it's not just that the machines get more powerful, their whole reason for existing changes. We go from a personal, one-to-one relationship with a microcomputer to a one-to-many deal with mainframes, and then back to a one-to-one relationship with supercomputers. But it's one machine versus one gigantic problem. So, we've looked at the scale of computers. Now let's dig a little deeper into how they actually process information. And this brings us to a really fundamental split. Does a computer measure the world, or does it count it? Okay, first up, the analog computer. This kind of computer works by measuring continuous physical things. A classic car's speedometer is a perfect example. It's not counting numbers. It's physically connected to the wheels, and the needle's movement is a direct measurement of their rotation. It's a direct representation of the real world, but it's always going to be an approximation. And then we have the digital computer. This is what we're all used to. A digital computer translates everything into numbers, specifically just ones and zeros. It doesn't measure, it counts. And that's what allows for incredible precision and the ability to store and copy data perfectly, which is pretty much why digital took over the world. So the key difference is this. Analog is a direct reflection of the continuous and often messy real world. Digital is an abstraction of that world, where everything gets converted into clean, precise numbers. You could almost say one is a mirror and the other is a map. So what happens when you need the real-time speed of analog and the pinpoint accuracy of digital? Well, that's where hybrid computers come in. They are basically translators, built to bridge the gap between continuous analog signals from the real world and the digital data a processor can understand. And this is just a brilliant illustration of that idea. In a hospital ICU, you've got analog sensors on a patient that measure the continuous wave-like signal of their heartbeat. That analog signal then gets piped into a digital processor, which counts it and turns it into a precise number, say 72 beats per minute, and slaps it on a screen. It's the perfect partnership, and it literally saves lives. All right, our final way of classifying computers asks the most basic question of all. Why? Why was this thing even built? Is it supposed to be a versatile, do-it-all toolbox, or is it a highly specialized, single-purpose instrument?
This gets us to that classic trade-off between versatility and specialization. Is this computer a jack of all trades, or is it a master of one? Your laptop is the perfect example of a general-purpose computer. The hardware itself is just a blank slate. It's the software you run that defines its job. One moment, it's a word processor. The next, it's a movie theater. And after that, it's a gaming console. It's one machine with 1,000 different jobs. A special-purpose computer, on the other hand, is born knowing its destiny. That tiny computer chip inside a washing machine, it has one job for its entire life: control wash cycles. It's never going to browse the internet. An ATM is just a computer whose only purpose in life is to securely give you cash. These devices are incredibly efficient because they've been stripped of everything that's not essential for their one single task. Okay, so we've got our three lenses: size, data handling, and purpose. The real magic happens when you realize these aren't just separate boxes. They're intersecting axes that let us pinpoint and define any computer that has ever existed. Let's apply our new matrix to the device you might be holding right now, your smartphone. What is it? By size, it's a microcomputer. By the way it works, it's digital. And by its purpose, it's general purpose. Boom. General purpose digital microcomputer. This framework gives us a super precise way to talk about any computer. So, by understanding these three axes, scale, data handling, and purpose, you've just been handed a powerful mental model for making sense of the entire digital world. It's a map that can help you understand not just the tech of today, but the tech of tomorrow too. And that leaves us with a final thought to chew on. These categories, they work beautifully for the computers we have today. But as we move into the age of quantum computing, or biological computing, or computers so small they're literally part of the fabric of our clothes, will these lines even hold? What will be the next great dividing line we use to map the future of computing? That's something to think about.